Hello and welcome to another video for pre-calculus. We are going to start a new chapter now, that is exponential and logarithmic functions. And in this video, we are going to discuss about the exponential functions. So before we start with the definition, let's look at this function 2 to the x and 2 to the negative x. Let's put this into the um, uh, graph, okay? So in order to graph this, and let's make a small a table of values for each of these functions. So let me say, okay, f of x equals 2 to the x. So let me make a small table for this. So I'll take some x values and I'll find some y values, okay? So let's take some negative values. So if I take x equals negative 2, that is 2 to the negative 2, which means 1 over 4. Okay, so it means if we have, so 2 to the negative 2 can be written as 1 over 2 squared using this rule. So if you have a to the negative m, by the rule of indices, you can write 1 over a to the m. Okay, so that's why this becomes 1/4. Now, let's take another value. Let's take negative 1. So when I take negative 1, I get 2 to the negative 1, which is 1/2. If I take 0, 2 to the 0, which is 1. If I take 1, 2 to the 1, which is 2. If I take 2, 2 squared, sorry, if I take x equals 2, then we get 2 squared, which is 4. If I take 3 to cube, which is 8, and so on. So we know what those values are. So when x equals negative 2, it's 1/4. So down here, okay. And then when we take x equals negative 1, it is 1/2. So let's say somewhere here. And then when x is 0, it is at 1. When x is 1, it is at 2. When x is 2, it's at 4. And when x is 3, it is at 8. So this is how the graph is going to look like, okay? So this is for f of x equals 2 to the x. Now similarly, if we make a table for f of x equals 2 to the negative x, and also remember 2 to the negative x can also be written as 1 over 2 to the x. With again the same rule, if we have a to the negative m, I can write 1 over a to the m. So if we have 2 to the negative x, we can write 1 over 2 to the x. And now I can put that exponent for 1/2 because 1 raised to x is just 1, so it really doesn't matter. So if you see 1 over 2 to the x, so this is same as 2 to the negative x, okay? Now, if we take the similar values here, so if we make a table here, I can take x and y values. So if I take x equals negative 2, now what happens is we have 2 to the negative x. So 2 to the negative 2 means that is 4. 2 to the negative of negative 2, which is 2 squared. That becomes positive. So now when I take negative 1, I get 2 to the negative of negative 1, which is 2. If I take 0, I get 1. If I take 1, I get 1/2. If I take 2, I get 1/4, and so on. So this is how it's going to look like. They have the same x-intercept, so it's right here. Then when I have negative 1, it is 2. When I have negative 2, the y value is 4. If I go to negative 3, the y value would be 8. And then when I move on to the right, at 0, 1, at 1, it is 1/2. At 2, it is 1/4, and it goes very close to the x-axis. So this is how the graph is going to look like. So this is f of x equals 2 to the negative x, or again it can also be written as 1/2 to the x, okay? So now if we look over here, one thing, it looks like the graph is getting closer and closer to x-axis, but one important thing is it is never going to touch x-axis, okay? It's getting very close to x-axis, but it's never going to touch x-axis. That means we don't have a x-intercept for these either of these functions, okay? So no x-intercept. So for the first function, none Okay, let me use blue for this one. Sorry. So for the first function, the graph is blue, so none. Okay, so there's no x-intercept. If you look at the y-intercept, it is right here 1, so we can write 0 comma 1 is the y-intercept. Now domain of this function, sorry, this is domain of this function is all real numbers. Now for the range, it's never going to touch x-axis and it's never going to go below that. So that means the range is from 0 to infinity, and 0 is not included because it's never going to become 0. It approaches 0, but it's never 0. Now horizontal asymptote is, we don't have any vertical asymptote here, but we have the horizontal asymptote, which is the x-axis or the line y equals 0. And then if we look on that blue line, blue curve, we see that when we go from left to right, the function is increasing, okay? Or we have to climb up. So that means the function is increasing. Now, similarly, for the other function, there's again no x-intercept, so x-intercept is none. The y-intercept is same, so 0 comma 1. The domain, again, it is an exponential function, so we have all real numbers. Range, same thing, 0 to infinity. Horizontal asymptote, y equals 0. Now, the purple graph, if you look over there, when we go from left to right, we have to climb down, or the function is decreasing. So this one is decreasing. So now if we just look at these functions, they look interesting. And then, so for example, if I write, so this is the point of doing this one. Okay, so if I write x squared, okay, we already know this is a polynomial function. We already talked about. We have a variable here as the base, and then the exponent is a real number or a constant. Now here we have 2 to the x. So the base is a constant and the exponent is a variable. So if we have something like this, a constant raised to a variable, those type of functions are called the exponential functions. And we can see that from the graph that exponential function either just increase or decrease, whereas polynomial function, you could see they are increasing and decreasing. You could see bends and turning points. So we don't have that with the exponential function. They just increase or they just decrease. Okay, so the purple one is a decreasing function, or we call that exponentially decaying function. Okay, and the blue one is exponential growth function. Okay, so it's increasing. So now here is the formal definition. Any function written in this form, f of x equals a times b raised to some power x, where x is a real number, a is a non-zero real number, and b is greater than 0, and b is not equal to 1, is called the exponential function. So it's very important that b is greater than 0. So we can go back to that function. So 2 to the x and then 1/2 to the x. Sorry, yeah, 1/2 to the x. Okay, so you might think that 1/2 is not greater than 0. It's still a exponential function, because we can write this as, so remember, we can write this one as uh, 2 to the negative x. That's why this is the standard form. We write b as a number greater than 0, and then we have that negative exponent. Okay, but this is not wrong. I mean, this is also an exponential function. So we really have to be, the definitions are more general, so we should not get confused when you look at the definition. Okay, now let's see what we have in the next slide. So now how to evaluate exponential function. So it's similar to any other functions. We will just substitute x for whatever we are evaluating the exponential function for. So in this case, f of 3 equals, so f of x equals 5 times 2 to the x. So f of 3 equals 5 times 2 to the third. And then 2 to the third is 8 times 5 is 40. We can also put this into the calculator. Okay, so this one equals f of the square root of 3 is 5 times 2 to the square root of 3. And then we can just put this into the calculator, because we really cannot do this by hand. So if we put this into the calculator, we get approximately 16.61. Okay, Similarly, f of pi is 5 times 2 to the pi. Again, we'll put this into the calculator and we get approximately 44.12. Similarly, this is 5 times 2 to the negative 1/4. And again, putting this into the calculator, we'll get approximately 4.20. Okay, so let me write approximate. It's not exact because we have so many decimal places after that. So this is how we evaluate any exponential function. It's similar to any other functions that we talked earlier. Okay. Now, here we are given 2 points, and if we are given 2 points, we can find the formula for the exponential function. We can really find the function if we are given at least 2 points, okay? So now let's go ahead and do that. So in order to find this one, we'll take the general form of the exponential function, which is y equals a b to the x. So this is the general form of the exponential function. Now we'll use the first point. X is 0, y is 6. So we can replace that here. 6 equals a times b to the 0 because x is 0. Now b to the 0 is 1. So this gives us a equals 6. Okay. Now let's use this second point. We will rewrite that equation. So y equals ab to the x. And then when we use second point, we have 750 as y equals, now we know the value of a because it's 6. So we can put that 6 times b to the x is 3. Now all we need to do here is find b and then we can write our function, okay? So here, first we divide by 6 on both sides. So when we divide by 6 on both sides, if we divide by 6, what we get here is we get b to the third equals 750 divided by 6 is 125. Now it's not that easy just looking over there what is the value of b, but what we can do here is, so we have b raised to third. If we can change this 125 into a number raised to the third power, then b must be equal to that number, okay? And just looking at 125, we can say that b cubed equals 125 can be written as 5 cubed. Now we have same exponent and we have a equal sign. That means this base must be same. So that gives us b equals 5. So we know a, we know b. Now finally we can write our function for this one. Let's write f of x equals a is 6 times b is 5 to the x. So this is the exponential function that goes through these 2 points. Now similarly, let's go ahead and do the next one here. Okay, so let's do the same thing. Let's use the first point. So our again exponential equation is y equals a b to the x. If we are using the first point, actually I made a correction here. This is should be a 16. Okay, so so we have y equals 16 equals a times b to the x is negative 2. It looks like we cannot do anything here. We have two unknowns, and then it's not like the first one. So we'll just call these as equation 1, and we'll just leave it here, okay? And then we'll use the another point. So we'll again write the same thing, y equals a b to the x. And then this point here, 1 equals, so a b to the x is 2, okay? So now we have 16 equals ab to the negative 2, and then 1 equals ab to the b squared. So this is equation 2. Now in order to find the values of a and b, what we are going to do is we are going to divide the second equation or equation 2 by equation 1. So divide equation 2 by equation 1. So if we do that, so the left hand side is 1 divided by 16 equals, the right hand side is ab squared divided by ab to the negative 2. Now we can cancel out a here. So this gives us, now what is b squared divided by b to the negative 2? So when we divide, if we have the same base, we subtract the exponent. So we have b squared, so b to the 2 minus negative 2, which means b to the fourth. So b squared divided by b to the negative 2 is b to the fourth equals 1 over 16. Now if we take the fourth root here, we get b equals, sorry, if we take the fourth root, we get b equals the fourth root of 1 over 16, which is 1/2. So we got the value for b. Now to find a, I'm just going to use this equation, which looks a little bit easier. So substitute b equals 1/2 in equation 2. If we do that, so we have a times b is 1/2 squared equals 1. Or this is a over 4, or a times 1/4, which is the same thing, equals 1. And if we multiply by 4 on both sides, so we get a equals 4. Now we have the value for b, we have the value for a. Now we can write our function as f of x equals a is 4 times b is 1/2 to the x. So the exponential function that goes through these 2 points is f of x equals 4 times 1/2 to the x. Now there are some characteristics of the parent function. So this actually f of x equals a b to the x is the standard form of the exponential function, but the parent function, remember, um, any function has a parent function, and from there, by doing some transformation, we'll get the other function. So the parent function is b to the x. This a is, we are just multiplying and we are just doing the transformation. Okay, we are doing the vertical stretch or shrink. That's what this a does. So the parent function for any exponential function is f of x equals b to the x. So there are some characteristics for this. Just looking at that function, we can say this, okay? So this function is 1-to-1. That means we have the inverse, which is a function. The horizontal asymptote for this parent function, not for the transform function. When we transform, this might change. The function might go down, might go up, depending on what transformation we do. But for the parent function, the horizontal asymptote is always y equals 0 or x-axis. Domain all real numbers, range 0 to infinity. There are no x-intercepts. Y-intercept is 0, 1, and it is increasing if b is greater than 1 and decreasing if b is less than 1. So remember, we just look at 2 to the x and then 1/2 to the x. So it's exactly the same thing. We can consider that function, whatever characteristics we wrote over there, it's the same thing. Okay, so these are the characteristics of the exponential function, the parent function. Now let's look at this graph. Okay, so we have a function 2 to the x, and then from that function we can find several other functions. So if we look at if we look at this function, and then if we compare this with 2 to the x, what we see here is we have x minus 2. That means we are subtracting a number from x. So remember, when we did the function transformation, we learned that if we subtract a number from x, the graph of that function shifts to the right. So the transformation here, the first thing that we need to answer is, what is the transformation? So the transformation is shift to the right. By how many units? It's 2 units, because we are subtracting 2. That's the first answer. Now let's go ahead and graph. So in order to graph this one, what I'm going to do is I'm going to use the parent function 2 to the x. So first I'll go ahead and graph 2 to the x, and then I'll graph the new function. Okay, so let's go ahead and graph 2 to the x. We already did that in the first example, so I'm just going to do that here. So it's 1/4, 1/2, 1, 2, 4, and 8. So this is the parent function, which is 2 to the x. So this is f of x equals 2 to the x. Now if we look at this function right here, g of x equals 2 to the x minus 2, that means this function is shifted to the right 2 units. So I can take every point on this red graph and I can just move that graph 2 units to the right. So if I pick this point right here, I can move that 2 units to the right, okay? And then if I pick the other point, I can do the same thing. I can move that point 2 units to the right. If I pick this y-intercept, so I move that 2 units to the right. And then I move this point 2 units to the right. I move this point 2 units to the right. And I move that point 2 units to the right, okay? So when I do that, this is how the graph of that function g of x equals 2 to the x minus 2 looks like. Okay, so that is the graph of the given function. Similarly, let's go ahead and do look at the next example. Again, here the transformation is we are subtracting a number from the function. That means the transformation is shift down 1 unit. Okay, and then let's go ahead and graph the parent function first. So again, the parent function is right here, here, 2, 4, 8. So this is the 2 to the x, the parent function. That's how it looks like. And then the new transform function here is we move the graph down 1 unit. That means if I pick this point here, this will go down. That point will move down here. Okay. And this point will go down here. So all these points will move 1 unit down. And this one will go here. So this is how the transform function or h of x equals 2 to the x minus 1 is going to look like. Okay, now we have to answer some of these things. So what is the domain? Again, for exponential function, the domain really does not change with the transformation. So it's always the domain is all real numbers. So domain is all real numbers. Same thing here, domain is all real numbers. Now the third question is what is the range? So if you look over here, the first one here, we just move the graph to the right. So it's not going to change the range. So the range is again 0 to infinity. Again, it's not going to change the horizontal asymptote. So it's still y equals 0. Here for the second function, the range is going to change because we move the graph down. So the horizontal asymptote here is this line right here. This is the horizontal asymptote, which is y equals -1. And the range is from -1 to infinity. Okay, since we move the graph 1 unit down, so the range will change. Similarly, the horizontal asymptote is the line y equals -1. Now let's look at an application of exponential function that we often see is the compound interest formula. So the compound interest formula is right here. So this formula, some of the notation here are, so first one is the amount or the value of the account, which is A of t. P is the principal or the initial investment that we do, or the initial deposit that we make. R is the rate of the interest. Okay, so it's this one very important that we need to express this one in decimals. Okay, so this is always written as decimal. So when I say decimal, if it is 25%, that means that is 0.25. This is how we put that into the formula. We don't put 25. Or if the interest is 8%, the rate is sorry, the interest rate is 8%, then we put 0.08. Okay, and is the number of compounding period in 1 year. That means if it is compounding annually or once in a year, n equals 1. If it is compounding every 6 months, n equals 2 because that gives us 2 compounding period in a year. If it is compounded monthly, n equals 12 because that is 12 times in a year. If it is daily, then n is 365 because we have 365 days in a year. So n changes depending on how often it is compounded. And the next letter that we have here is t. T is the how long do we deposit that? And T is the time measured in years. Again, if it is in months, we need to change that in a year. Okay, so two important things here. R should be in decimal and T should be in year. So that's very important when we put this into the formula. Let's look at an example here. So we are going to look at this example here. So we have the question is find the future value or the amount, okay, of 10,000 placed in an account earning 8%. So this is the deposit that we make, the initial deposit. This is called the principal, or this is P, okay? And then the interest rate is 8%. That means when we change this to decimal, it is 0.08. That's what we are going to put in the formula. So R equals 0.08, P equals 10,000. For 10 years means T is 10,000. Okay, sorry, T is 10. If the interest is compounded, so we have a couple of things that we need to do. So the first one is if the interest is compounded annually, annually means once in a year. So N equals 1 for this one. Semi-annually means twice a year. So N equals 2. Quarterly means every 3 months or 4 times in a year. So N equals 4. Monthly means every month or 12 times in a year, so N equals 12. So P, R, and T are not going to change for A, B, C, and D, but N is going to change. And then that makes a difference to the value of the amount. Okay, so what will we have at the end? So let's go ahead and write the formula here. So our formula is A of T equals P times 1 plus R over N to the NT. So this is the formula. Now for A, we have N equals 1. So for A, amount after 10 years, so A of 10, A of T means A of 10 here, equals principal is 10,000 times 1 plus 0.08 is the interest rate divided by n. So for A it says annually, so n is 1 to the n times t. N is 1, t is 10. So 1 times 10 is 10. And then we can put the whole thing into the calculator, and I have already calculated that. So this gives us $21,589.25. Now let's look at the next one, B. This is semi-annually, so n equals 2. So the amount after 10 years, which is 10,000, 1 plus 0.08. Now in this case, n is 2 because it's twice a year. So you really have to be careful here. This is not just time, okay? The exponent is n times t. So in this case, we have n equals 2 and t equals 10. So this becomes 20. And then when we put that into the calculator, we are going to get 21,911.23. Okay. Now let's look at the next one, C. For C, it says quarterly. That means 4 times in a year. So the value after 10 years equals 10,000 times 1 plus 0.08 divided by, so now n is 4 to the, now be careful again, the exponent is n times t. N is 4, t is 10, so this becomes 40. And then when we put the whole thing into the calculator, this is what we get, $22,080.40. Okay, now D, let me use a different color here. So D is monthly. That means n is 12. So the value after 10 years, if compounded monthly, is 10,000 times 1 plus 0.08. Now n is 12. To the, again, just be careful, the exponent is n times t. N is 12, t is still 10. So 12 times 10 is 120. And then when we put this into the calculator, we get $22,196.40. So now what we notice here, if you look at these numbers carefully, we notice that as we increase the as we increase the compounding period n, then we get the value is more and more. So if we that just means that we are getting the interest frequently, and then our value changes frequently, or it increases quickly. Okay. Now there's a special exponential function with a special base. Okay, so there's an exponential function with a special base, which is e. Again, this e is not a variable, it's a number, which is called Euler's number. And the value for that one is this one. So actually the definition of e is 1 plus 1 over n to the n when n increases without bound, or when n approaches infinity. This is what we write in calculus. Okay, so limit n approaches infinity of this one. That means when n is very, very large, the value of this number is a number which is e. Okay, so that's the Euler's number. So now an exponential function with this base e is called the natural exponential function. Okay, and which is very important. It has a variety of applications, and we use this a lot. Now, our calculator, any calculator, TI-84 or TI-83 calculator, will have a key on the calculator where we can find. So if we have e to the some power, then we can just find that from the calculator. So in your calculator, if you go to second and then ln, then when you hit this, if you hit second and ln, this is what you see in your screen. You'll see e to the box. And then in that box, you are going to put this whatever the exponent is. So for example, the first one is 3. And then if you hit enter, okay, and that's going to give us 20.0855. So again, you hit second, ln, that's what comes up in the screen. We put the number here in the box, whatever number, whatever exponent we have here, these numbers, we'll put that in the box, and we hit enter, and that's what we'll get the value for that one. Okay, so the first one is we'll get 20.0855 when we put that into the calculator. Okay, so we'll use calculator to find this one. There's no way we can find this by hand. Okay. And when we put this into the calculator, we get 0.7866. E to the 0, you don't have to put it into the calculator because we know that any number raised to 0 except 0 itself is 1. So e to the 7.3 is 1480.2999. Okay, so this you try to use this calculator to find these values, because this is something that we use a lot in math. Okay. Now these are exponential function. So let's look at the graph of e to the x. So if you want, you can make a small table. Use your calculator to make the table, and then we can graph this. And so, for example, for the first one, so if we have e to the, so for this one, okay, the first one, x and e to the x. Okay, so if we take x equals -2 and then use the rule that we did in the previous example, put it into the calculator. So if you put e to the -2 in the calculator, then you get 0.135. So this is 0.135. Similarly, if we put -1, we get 0.368. Okay, there are more decimal places. I'm just rounding to 3 decimal places. If we put 0, then 1. If I put 1, we get 2.718 and goes forever. If we put 2, we get 7.389 and then goes forever. And if we put 3, then I think it's a really huge number. Okay. Now, when we put that into the graph, so it is very small number here, increases a little bit. The y-intercept is 1, and when it is 1, it is 2.78, which is close to 3, somewhere here. And when we put 2, 7.3 something, so it's just somewhere here. Okay, I'm just approximating. So this is how the graph of e to the x looks like. So f of x equals e to the x, and it goes forever. Now again, it's similar to any other exponential function that we already talked. So we have the domain, all real numbers, range 0 to what infinity, and then y-intercept is 1. There's no x-intercept, so this is the basic e to the x function, and the properties are similar to what we discussed already. Okay. Now this function right here, the one that you see here, is the transform form of that one. So we are adding a number to 3. That means our graph moves to the left. Okay. So now let's just use this first graph to graph that function. We don't have to make a table. What I'm going to do is I'm going to look over here. So let's consider this point here. This graph is moved to the left. So move or shift or move to the left. Okay. That's what we are going to do. We are going to move that graph to the left. So when we move that one to the left 3 units, so one from here goes 1, 2, 3. So it comes right here. And then we have a smaller value here, a smaller value here to the left. Okay. And then similarly, if we look at this point here, which is 2.718, 1 will move to the left 3. So 1, 2, 3. So somewhere here. Similarly, if we move that point, 7 point something that we have for x equals 2. So this point here will, if we move that to the left 3 units, so we get 1, 2, 3 somewhere here. Okay. And then that's how it's going to look like. So this is g of x equals e to the x plus 3. And then if you keep checking, the y-intercept is 20 point something. Okay, so when x is 0, we got e cubed. So the y-intercept is 20 point something here, up, way up from there. Okay. Now we discussed about the compound interest earlier. We had some compounding period, and then we can find the compound interest using p times 1 plus r over n to the nt. Now, when n approaches infinity, or when n becomes very large, okay, now what happens is this thing here will change. Continuous means there is no any period. It's like you put your money, starts growing instantly and keeps growing every moment. Okay, so there's no any period. It's not like you don't have to wait. So if you put your money, after a few seconds, if you go ahead and check, you should see some interest. Okay, so it's growing continuously. There's no break. You don't have to wait for any period. So that is continuous. So if the money is growing continuously, compounding continuously, then this is the formula that we use versus the formula that we have over here. Okay, so this is for the one that has compounding periods, so daily or monthly. That's when you are going to get your interest. But when it is continuous, you are getting interest instantaneously, continuously. Okay. So this is the formula that we are going to use. Again, it's very similar. P is the principal or the initial amount that we deposit. R is the rate. Again, it has to be in decimal. T is the time. Again, it's in year. Okay. So let's go ahead and look at an example for this. So here's the deposit that we are making. So this is the principal invested for that much. See, this is how you know from the question which one are you doing compounded with the periods or continuous. So the question will say continuous. If it is compounded at some period or periodically, then the question says compounded quarterly or annually or semi-annually or daily or hourly, whatever. It has some period. Okay, but this one, it says continuously. That means we know this is compounded continuously. Okay, so this is P. This is the rate, but remember we have to change that to decimal, so 0.04, and then this is the time t. Now, the formula, the value of this amount equals p e to the r t. A after 3 years, so t is 3 equals principal is 15,000, e to the r is 0.04 times t is 3. Now we can just put this into the calculator. So if we put that into the calculator, this is what we are going to get. So when you put that in the calculator, you get 16,912.45 dollars. So this is the future value. But what the question is asking us is to find the interest earned. That means we deposited 15,000. After 3 years in our account, we see 16,912.45. That means the interest that we earned. Okay. is given by this value, the present value or the future value, minus the principal or the initial amount that we deposited. So this is 16,912.45 minus 15,000 is the principal, and then when we subtract that, we get $1,912.45. So this is the interest earned based on this scenario. Let's look at one more example of exponential function, the application. Okay, so this type of problem, this type of function, usually this is called logistic growth. Okay, sometimes we use this for even some logistic population growth or something, but here it is about the growth of the disease, growth of the infected people. Okay, so we have a total population of 40,000. Some people are infected, and the disease is spreading, just like we have the coronavirus pandemic, right? So it's similar. So it's just growing. Okay, so it's spreading very quickly. So now this function represents that is spread. Okay, so how many people are infected after each day? So here t is not the time in year, this is time in day. Okay, so every day, so after 2 days or after 3 days or after 7 days or after 20 days, how many people are infected? So the first question is asking us how many are initially infected. Initially means at time t equals 0, or the first day. Okay, the first initially means we use t equals 0. Okay, so how many people are infected initially? So for A, we have to find n of 0. So t equals 0 for this one, initially means. Then we have 40,000 divided by 1 plus 19.9 e to the, now when t is 0, negative 0.6 times 0 is 0. Now e to the 0 is 1, so we just have basically 40,000 divided by 19.9 plus 1 is 20.9. And then if we put that into the calculator, I think I have the value here calculated. So we are going to get 1913.86, but it's number of people, or how many people are infected, so we can write that as a decimal. So we always round this up. Okay, so we'll approximate this as 1914. So that many people were infected initially. Now, after that, so how many people are infected after 2 days and 7 days? So that's the second part of the question. So how many people are infected after the second day of the epidemic? Okay, so here we put t equals 2. So we have 40,000 divided by 1 plus 19.9 e to the, now when we put t equals 2, we get negative 1.2 because it's negative 0.6 times 2. Okay, and then if we put this into the calculator, we get 5949.999, which means this is 5950. That means after second day of the epidemic, 5,950 people are infected. See how quickly that's moving up. So let's check the other one. So n of 7. So let's see how many people are infected after day 7. Okay. So again, we just put everything into the calculator. So that gives us 1 plus 19.9 e to the negative 0.6 times 7. Now, if you put this into the calculator, this is what we get. So we get 31,130.44. That means approximately 31,131 people are infected after day 7. See, within 7 days, almost all population is infected. So the total population is only 40,000. Now, if you keep going on, you see that increase. Now, the third question is asking us to graph this function, and I already used the Desmos to graph this one, and I have copied the graph here. So it looks like this. This is the y-intercept, which is the initial infected number, okay, which is 1,914. And then if you look over here on the graph, so it goes exponentially, it grows so quickly, and at it approaches 40,000, it slows down a little bit, and then it reaches the maximum value. So it cannot go above 40,000 people, because it cannot go above 40,000 because that's the total number of people that we have, the population. So it cannot infect more than the population that we have. So this is eventually goes that way. Okay. So here we can say that the graph approaches the line. So the graph, we can say the graph increases, okay, quickly, and approaches 40,000. Okay. And which is the max. So 40,000 is the max for this graph. So that's the maximum that the function can reach. Okay. We'll just do this much for this video. In the next video, we'll talk about the logarithmic function.